Hello, and welcome to the Sleepy Curiosity channel. As you find a comfortable position, let your body start to release the weight of the day. If this gentle journey is already beginning to slow down your thoughts, consider subscribing now, so these stories can keep finding you, night after night. Now, let the relaxation settle into your breath. The ocean covers more than 70% of the Earth, and less than 25% of it has been explored by science. The largest environment on our planet is, at the same time, the most unknown one there is. Every time we approach it with better instruments, it reveals something we didn't expect to find: a new species, a current that shouldn't exist, a form of life that survives where surviving seems impossible. And the more we observe it, the more remarkable it becomes. There's a question that seems to have an obvious answer, but that scientists still debate seriously. Where did the water in the oceans come from? The Earth, when it was young, was a planet of molten rock and extreme heat, and not a single drop of water could have existed on its surface at that time. The most widely accepted hypothesis today points to two simultaneous pathways. Some of the water came from inside the Earth itself, released by volcanoes over millions of years in a process called outgassing. Another portion arrived from outside, carried by asteroids and comets rich in ice that bombarded the young planet during the period known as the Late Heavy Bombardment, roughly 4 billion years ago. The detail that makes this story even more interesting is the ratio of hydrogen isotopes in ocean water. When scientists compare that ratio with those of different types of asteroids, the results suggest that carbonaceous chondrite asteroids were likely the main suppliers. Comets, contrary to what was once believed, have a different isotopic ratio, which reduced their role in the explanation. In other words, the water that covers 71% of Earth's surface arrived, in large part, from space. Imagining the ocean as something that always existed the way we know it today is an interesting mistake. It went through transformations so radical that the primitive ocean and the current one barely seem to belong to the same planet. After the gradual cooling of Earth's crust, the water vapor that saturated the primitive atmosphere began to condense. The first rains that fell on Earth lasted, according to some estimates, thousands of years, and it was those rains that filled the initial ocean basins. That primordial ocean was warmer, with a distinct chemistry, no dissolved oxygen, and probably a greenish hue due to the mineral composition of the water. Oxygen only began to accumulate in the ocean when primitive photosynthetic organisms, cyanobacteria, appeared around 2.7 billion years ago. This process, called the Great Oxidation, completely transformed ocean chemistry and made it possible for more complex life forms to emerge. The ocean, therefore, is not just a backdrop. It's a system that co-evolved with life itself. Maps show 5 oceans with distinct names: Pacific, Atlantic, Indian, Arctic, and Antarctic. But from a physical and hydrological standpoint, that division is a human convention. The water doesn't recognize those borders. All the oceans are continuously connected, exchanging water, heat, salt, and organisms without interruption. The thermohaline circulation moves water between the Atlantic, the Indian, and the Pacific in a cycle that takes about 1,000 years to complete. No physical barrier separates these bodies of water. The divisions are geographic, based on continents and arbitrary meridians. The Antarctic Ocean was only officially recognized in 2000, and it was defined not by a physical barrier, but by a current that creates conditions so distinct that they justify treating it as a separate entity. In practice, the Earth has a single continuous ocean, with peninsulas of land rising out of it, not continents surrounded by separate seas. The ocean floor seems like the most unchanging place on the planet. In reality, it's one of the most dynamic, and no piece of the current ocean floor existed more than 200 million years ago. This happens because of plate tectonics. The ocean floor is constantly being created at mid-ocean ridges, chains of underwater mountains where two plates move apart and magma rises to fill the gap. As that material cools and moves away from the ridge, it slowly drifts until it reaches a subduction zone, where it dives back into the Earth's mantle and is recycled. The ocean floor is, geologically speaking, much younger than the continents. Continental rocks more than 4 billion years old have been found, but no rock from the ocean floor exceeds 200 million years. The ocean is literally renewing itself on a geological scale. And the Atlantic is still expanding a few centimeters every year. Seawater has, on average, 35 grams of salt per liter. That might seem like a simple detail, but the origin of that salt reveals a lot about how the planet works. The process begins on the continents. Rain, slightly acidic by nature, dissolves minerals from rocks along rivers and streams. Those dissolved minerals are continuously carried to the ocean. Once there, the water evaporates, but the salts stay behind. Over billions of years, that concentration kept building up. Underwater volcanoes also contribute, releasing compounds rich in chlorine and sulfur directly into the water. What's curious is that ocean salinity appears to have been relatively stable for hundreds of millions of years, which suggests that balancing mechanisms exist, such as the precipitation of minerals on the seafloor and absorption by marine organisms, that offset the continuous addition of salt. In that sense, the ocean has a kind of long-term chemical self-regulation. Looking at the ocean from the surface gives the impression of uniformity. But dividing it vertically, what you find are environments so different from one another that they could belong to separate planets. The uppermost layer extends to around 200 meters deep, where sunlight penetrates with enough intensity to support photosynthesis. Below it begins a zone of growing twilight, rising pressure, and sharply dropping temperatures. Beyond 1,000 meters, light disappears completely, total darkness, temperatures near 4 degrees Celsius, pressure equivalent to hundreds of atmospheres. Even further down are the abyssal zone, between 4,000 and 6,000 meters, and the hadal zone, which includes ocean trenches and can exceed 10,000 meters in depth. Each of these zones has such distinct physical, chemical, and biological conditions that organisms adapted to one of them generally wouldn't survive in another. The ocean, in the vertical direction, is a collection of overlapping worlds. There's a boundary in the ocean that doesn't appear on any map, has no visible color or shape, but divides the water column so effectively that submarines use it as an acoustic shield and fish rarely cross it. The thermocline is a layer where water temperature drops very sharply over a small vertical distance, sometimes 10 degrees Celsius or more in just a few dozen meters. It exists because sunlight warms only the surface layer, and that heat doesn't transfer easily to the deeper waters due to the density difference between warm and cold water. During World War II, submarines learned to dive below the thermocline to escape enemy sonar, since the layer refracts and scatters sound waves. That same principle is still relevant in modern oceanography. The thermocline acts as a natural acoustic mirror inside the ocean. The pressure at the bottom of the ocean is one of the hardest physical phenomena to visualize from the surface. For every 10 meters of depth, pressure increases by approximately 1 atmosphere. In the Mariana Trench, at roughly 11,000 meters deep, the pressure reaches more than 1,000 atmospheres. For a concrete reference, a styrofoam cup taken to that depth comes back the size of a marble. The air trapped in the foam's bubbles is compressed to the point where the material permanently shrinks. Metal objects deform, and instruments have to be designed with thick walls to withstand the crushing force. What's most remarkable is that life doesn't just survive under that pressure, it has adapted to it in extraordinary ways. Abyssal organisms have cell membranes with a different composition than surface species, with more unsaturated fatty acids that maintain fluidity even under intense compression. The pressure that would destroy a human diver in seconds is, for certain forms of life, simply the normal environment. The average temperature of the deep ocean is around 2 degrees Celsius, close to the freezing point, but not below it, because salt lowers water's freezing point. That stability exists because deep waters form in polar regions, where surface water cools, becomes denser, and sinks to the bottom. But the deep ocean also holds dramatic exceptions. At hydrothermal vents, the water expelled through underwater chimneys can reach 400 degrees Celsius, without boiling, because the extreme pressure raises the boiling point far above 100 degrees Celsius. The temperature difference between the fluid coming out of the chimney and the surrounding water can be nearly 400 degrees within just a few centimeters. That extreme contrast creates temperature gradients that fuel entire ecosystems with no dependence on sunlight whatsoever, making hydrothermal vents one of the most unusual environments known on Earth. Sunlight is the engine of almost all life on Earth. In the ocean, it penetrates, but far less than most people imagine. In clear tropical waters, about 1% of surface light still reaches 200 meters deep. Below that, there's no usable light for photosynthesis. The mesopelagic zone, between 200 and 1,000 meters, is called the twilight zone. It receives enough light for some organisms to detect it, but not enough to sustain plants or algae. It's an environment of deep blue that gradually darkens to complete black. This zone is estimated to contain the largest fish biomass on the planet, much of it still unknown. One of the most fascinating behaviors tied to this zone is the daily vertical migration. Millions of tons of organisms rise to the surface at night to feed on plankton, then descend back into the twilight during the day to escape predators. This migration is the largest daily animal movement on the planet in terms of biomass, and it transports carbon, helping to regulate the global climate in ways that scientists are still working to quantify. Looking at the ocean from above, the surface seems like a passive body of water, moved only by wind. In reality, it's organized into circulation systems with patterns so predictable that navigators used them centuries before any scientific explanation existed for them. Surface currents are driven primarily by wind, but their direction doesn't simply follow the wind, it's deflected by the Coriolis effect, caused by the Earth's rotation. In the northern hemisphere, currents flow clockwise, in the southern hemisphere, counterclockwise. These large circular systems are called ocean gyres, and there are 5 major ones on the planet. The Gulf Stream carries warm tropical water along the eastern coast of North America toward Europe. It moves a volume of water estimated at 30 times the combined flow of all the world's rivers. Its influence on European climate is so significant that without it, the average temperature of northwestern Europe would be several degrees lower than it is today. There's an ocean current that isn't driven by wind, isn't visible at the surface, and takes about 1,000 years to complete a cycle, but that regulates the climate of much of the planet more deeply than any surface current. It's called the thermohaline circulation, and it works on differences in temperature and salinity between water masses. In polar regions, surface water cools and becomes denser. If it's also saltier, which happens when ice forms and expels salt, that water sinks to the bottom and begins moving slowly toward the tropics. There, it gradually warms, rises, and returns to the poles along the surface, completing the cycle. This system works like a global conveyor belt, distributing heat across the oceans. The current scientific concern is that global warming is adding fresh water to the ocean through melting ice, and fresh water is less dense, which could weaken the polar sinking mechanism. Recent measurements suggest the thermohaline circulation is already weaker than at any point in the last 1,000 years. Tides seem like a simple phenomenon. The water rises and falls twice a day. But the mechanism behind them involves gravity, geometry, and the elastic response of an ocean that covers 2/3 of the planet. The Moon exerts a gravitational force on the Earth that isn't uniform. The side of the planet facing it is pulled with greater intensity than the opposite side. That difference in pull creates two bulges of water, one facing the Moon and one on the opposite side. As the Earth rotates beneath those bulges, different points along the coast experience high tide. The Sun also contributes, with about 46% of the Moon's tidal force, and when both are aligned, their forces add up to produce the most intense tides. What's less commonly known is that tides don't only affect the oceans. The solid Earth's crust also deforms in response to the Moon's pull, rising and falling up to 40 centimeters twice a day in a phenomenon called Earth tides. The entire planet breathes, imperceptibly, in rhythm with the Moon. Most people know ocean waves as the kind that arrive at the beach, generated by wind, visible, predictable. But there's another type of wave in the ocean, completely invisible from the surface, that can be hundreds of times larger than any surface wave ever recorded. Internal waves form at the interface between water layers of different densities, especially at the thermocline. When a tidal current pushes water over a rise in the seafloor, it can create an oscillation at the boundary between the layers. These waves travel slowly, but with amplitudes that can exceed 200 meters of vertical height. They're invisible because they occur inside the ocean, far from the surface. They only become detectable by satellite thanks to a subtle secondary effect. They modulate the surface roughness in ways that alter how sunlight is reflected, creating visible streaks in radar imagery. For submarines, internal waves represent a real hazard. They can drag a submarine up or down hundreds of meters in minutes. The ocean is not just affected by climate, it's one of its primary regulators, and it does so through several simultaneous mechanisms that make Earth's climate system far more stable than it would be on a planet without oceans. The first mechanism is thermal capacity. Water absorbs heat much more efficiently than land or air. The ocean has absorbed more than 90% of the extra heat generated by the increased greenhouse effect over the past few decades. The second mechanism is evaporation, which transports heat from the tropics to higher latitudes as vapor condenses into rain. The third mechanism is carbon absorption. The ocean absorbs about a quarter of all co-emitted by human activities, removing it from the atmosphere and slowing down warming. But that absorption acidifies the water, with consequences for organisms that depend on calcium carbonate to build shells and skeletons. The ocean is protecting us from an even more unstable climate, and paying a steep price for it. Seawater is not simply water with salt. It's a solution with dozens of dissolved elements, maintained in remarkably stable proportions across all the world's oceans, a chemical balance that took billions of years to establish. The main components are chloride and sodium, which together forms sodium chloride, common table salt. But seawater also contains magnesium, sulfate, calcium, potassium, and dozens of elements in smaller concentrations, including gold. The oceans are estimated to contain around 20 million tons of dissolved gold, in concentration so low that economically viable extraction is still far from reality. One remarkable characteristic is that the ratio among the major dissolved ions is virtually the same in any seawater sample from anywhere in the world, indicating that the oceans are well mixed on a global scale. And the blood plasma of vertebrates bears ionic similarities to primitive seawater, a legacy of our ancestors' marine origins. Seawater is slightly alkaline. Its current average pH is approximately 8.1. That number might seem irrelevant, but for marine organisms that depend on a precise chemical balance to build shells and skeletons, a variation of a few tenths of a unit has serious consequences. Since the Industrial Revolution, the average pH of the oceans has dropped from 8.2 to 8.1. Because it's a logarithmic scale, that represents an increase of about 26% in hydrogen ion concentration, an ocean significantly more acidic than it was 200 years ago. The mechanism is straightforward. When atmospheric co-dissolves in seawater, it forms carbonic acid, which releases hydrogen ions. Those ions react with carbonate ions, exactly the ones that corals, oysters, and many plankton species use to build their calcium-based structures. Experiments show that oyster larvae exposed to current acidity levels already struggle to form shells. For coral reefs, acidification represents an additional threat on top of heat-induced bleaching, and both pressures are happening at the same time. The oxygen in the ocean doesn't come only from the atmosphere. Much of it is produced by phytoplankton during photosynthesis, in the sunlit surface layers. That oxygen dissolves in the water and is consumed by organisms throughout the entire water column. In the deep where light doesn't reach, oxygen isn't replenished by photosynthesis. It's consumed by bacteria decomposing organic matter that sinks from the surface, and is only renewed when deep currents bring oxygenated water from polar regions. That process is slow, and in some areas, demand outpaces supply. Beyond naturally occurring low oxygen zones, the world has seen a troubling growth in coastal dead zones, areas where excess agricultural nutrients fertilize phytoplankton so heavily that when it dies and decomposes, oxygen is completely consumed. The result is an anoxic environment where fish and benthic organisms die en masse. Since the 1960s, the number of identified coastal dead zones has grown from a few dozen to more than 700. On certain nights, in the right waters, the ocean glows. Waves breaking on the beach leave trails of blue-green light, and every movement in the water seems to ignite small sparks. This phenomenon isn't a reflection of the moon or an optical effect, it's produced by living organisms. Bioluminescence is the ability to produce light through chemical reactions. In the ocean, it's extraordinarily common, it's estimated that more than 75% of marine species living below 200 meters are capable of producing light. The reaction involves a molecule called luciferin, which when oxidized releases energy in the form of visible photons, with far greater efficiency than any human-made lamp, generating almost no heat in the process. The uses of bioluminescence are varied. Some organisms use it to attract prey, like the deep-sea anglerfish with its luminous lure dangling above its head. Others use it to disorient predators. Some species produce light on their bellies to match the faint illumination coming from above, making themselves invisible to predators below them. The glow that appears on beaches usually comes from dinoflagellates, single-celled organisms that emit light when mechanically disturbed. The sea that glows at your touch is, literally, millions of cells responding to the movement of the water. Seawater is denser than fresh water, a difference that seems small in numbers, but that has profound physical consequences for ocean dynamics. Cold, salty water is denser, warm water with less salt is less dense. That difference means water masses with distinct characteristics don't mix easily, they stratify, with the denser one sinking and the less dense one staying on top. When fresh water from rivers enters the ocean, it doesn't mix immediately. Because it's less dense, it floats on top of the salt water for considerable distances before fully blending in. The Amazon River projects a plume of fresh water into the Atlantic that can be detected hundreds of kilometers from its mouth, an invisible boundary between two worlds within the same sea. The question of where life began on Earth still doesn't have a definitive answer, but the ocean is the strongest candidate, and within it, two scenarios compete for scientists' preference with equally compelling arguments. The first scenario points to hydrothermal vents on the ocean floor. At these underwater chimneys, hot water rich in minerals creates temperature and chemical gradients that could have provided the energy and raw materials for the first biochemical reactions. The second places the origin of life in shallow pools near the coast, where cycles of evaporation and rehydration would have concentrated organic molecules. What scientists agree on is that the first life forms were simple, single-celled, and probably very similar to the archaea and bacteria that still inhabit the most extreme environments in the ocean today. Everything that came after, plants, fungi, animals, human beings, is a branch of something that began in the water. There's a layer of life in the ocean that's invisible to the naked eye most of the time, yet sustains virtually the entire marine food chain and produces half the oxygen we breathe. It's made up of plankton, organisms that share one simple characteristic: they don't control their own horizontal movement, letting the currents carry them. Phytoplankton is the photosynthetic fraction of this group. Made up mainly of microalgae and cyanobacteria, it's responsible for about 50% of all photosynthesis on the planet, more than all the tropical forests combined. Zooplankton, in turn, is the animal fraction: copepods, krill, fish larvae, tiny jellyfish. Antarctic krill is so abundant that its total biomass is estimated at 400 million tons, and it's the primary food source for blue whales, penguins, seals, and albatrosses simultaneously. One detail that surprises many: much of the carbon fixed by phytoplankton at the surface sinks to the ocean floor when those organisms die, in a process called the biological carbon pump. This mechanism removes CO from the atmosphere and stores it in the deep for centuries, making plankton a central player in global climate regulation. The idea of a linear food chain, phytoplankton eaten by zooplankton, which is eaten by small fish, which is eaten by larger fish, is a useful simplification, but one that hides a far more complex and surprising web of relationships. One of the most counterintuitive links is the role of bacteria. Enormous quantities of dissolved organic matter in the ocean are consumed by bacteria, which are consumed by protozoans, which are consumed by zooplankton. This circuit, called the microbial loop, recycles organic matter that would otherwise be lost, and it was only discovered in the 1970s and 1980s. Another surprising link is that of whales. Beyond being predators, they act as nutrient pumps. They dive deep to feed and defecate at the surface, releasing nitrogen and iron that fertilize phytoplankton. And then there's the ocean's greatest paradox: the blue whale, the largest animal ever recorded on Earth, reaching up to 30 meters in length, feeds almost exclusively on krill, a crustacean just a few centimeters long. The largest animal on the planet depends on one of the smallest links in the chain. Coral reefs occupy less than 1% of the ocean floor, yet they shelter around 25% of all known marine species. That density of biodiversity has no parallel in any other marine ecosystem. Coral itself is an animal, a small, translucent polyp that lives in colonies and builds an external skeleton of calcium carbonate. What gives the reef its color and much of its productivity are zooxanthellae, microscopic algae that live within the polyp's tissue in a symbiotic relationship and provide the coral with up to 90% of its energy through photosynthesis. When water temperature rises above a critical threshold, the coral expels the zooxanthellae. Without them, the tissue becomes transparent and the white skeleton shows through, what we call bleaching. The coral doesn't die immediately, but it becomes severely weakened. The Great Barrier Reef experienced mass bleaching events in 2016, 2017, 2020, and 2022. What took centuries to grow can disappear in decades if conditions keep deteriorating. Migration is a common phenomenon in many animals, but in the ocean it reaches scales that are hard to imagine from the surface. Some of the longest journeys ever documented in nature happen beneath the sea. The leatherback sea turtle can migrate more than 20,000 kilometers between its feeding areas in the North Pacific and its nesting beaches in Southeast Asia, navigating without GPS, guided by Earth's magnetic field. Humpback whales make one of the best documented migrations among marine mammals. they leave the krill-rich waters of Antarctica heading toward tropical waters, covering roughly 8,000 to 10,000 kilometers each way. During that journey, they barely eat, living exclusively off their fat reserves. The whale shark can travel more than 20,000 kilometers on routes that cross entire oceans. For an animal that can measure 12 meters, that scale of movement still surprises researchers trying to understand how it navigates. Above 4,000 meters deep, the abyssal ocean seems like a desert, temperatures near zero, crushing pressure, total darkness, and few nutrients. For a long time, it was believed nothing could live there. The reality uncovered over the last 100 years is quite different. Fish like the tripod fish rest on the seafloor using 3 rigid fin extensions, remaining motionless for hours waiting for the water current to bring food to them. Abyssal animals often have very large eyes to capture any trace of bioluminescent light, or are completely blind, compensating with sensory systems that detect vibrations and chemical signals with remarkable precision. Many have flaccid, gelatinous bodies, without the rigid structure needed at the surface, but perfectly functional under high pressure. Brought quickly to the surface, these organisms simply fall apart. Their bodies are literally built for an environment that doesn't exist above certain depths. In 1977, a scientific expedition in the Pacific made a discovery that fundamentally changed biology. Descending to nearly 2,500 meters near the Galapagos Islands, researchers found something nobody expected: a lush, dense, and diverse ecosystem, in complete darkness, with no connection to photosynthesis whatsoever. Hydrothermal vents are fissures in the ocean floor through which superheated water rich in chemical compounds is expelled. Chemosynthetic bacteria use those compounds as an energy source, fixing carbon without sunlight in a process called chemosynthesis. Those bacteria form the base of an entire food chain that includes giant tube worms, crabs, shrimp, octopuses, and fish. The tube worms of hydrothermal vents are particularly fascinating. Some reach 2 meters in length and have no mouth, stomach, or digestive system. All their nutrition comes from bacteria living inside a specialized organ called the trophisome. This discovery dramatically expanded the definition of where life is possible, and increased scientific speculation about the possibility of life in the subsurface oceans of moons like Europa and Enceladus. The ocean is an environment where cooperation between species has reached forms of sophistication we're still learning to understand. The relationship between the clownfish and the sea anemone is probably the most well-known. The anemone uses stinging cells to paralyze prey, but the clownfish lives among its tentacles without being harmed, coated in a special mucus that mimics the anemone's own chemistry. In return, the fish cleans the anemone, drives away predators, and its waste fertilizes the algae the anemone also needs. Less known, but equally impressive, is the symbiosis between the pistol shrimp and the goby. The shrimp, nearly blind, digs and maintains a burrow in the seafloor. The goby, with sharp eyesight, stands guard at the entrance. The two maintain constant physical contact. The fish touches the shrimp with its tail. When the goby detects a predator and darts away, the shrimp receives the signal through that touch and retreats into the burrow immediately. It's a mutual defense partnership with real-time tactile communication. At the microscopic level, the symbioses are even more radical. Mitochondria, the structures that produce energy in all eukaryotic cells, are descendants of bacteria that were engulfed by ancestral cells roughly 2 billion years ago and never left. The origin of that symbiosis was, in all likelihood, in the primitive ocean. Intelligence, as a biological phenomenon, evolved independently in several branches of the tree of life. In the ocean, two groups stand out for cognitive abilities that challenge the expectations of anyone who associates intelligence only with land-dwelling mammals. Octopuses have around 500 million neurons, 2/3 of which are in their arms, allowing them to solve problems semi-autonomously, without fully relying on the central brain. Octopuses open jars with lids, navigate mazes, use objects as tools, and display something that looks very much like play behavior. All of this with a nervous system that evolved in a completely independent way from that of vertebrates. Dolphins recognize themselves in mirrors, use individual names for one another in the form of unique whistles, teach hunting techniques to their young, and form multilevel social alliances with a complexity comparable to that of primates. Humpback whales compose songs that change over time and spread between populations, a phenomenon that some researchers compare to the cultural transmission of information. The ocean is the least explored environment on the planet. Recent studies suggest that between 700,000 and 1 million marine species exist on Earth, and that only around 240,000 have been formally described and named. That means potentially more than half of all marine biodiversity is unknown to science. Every expedition to the deep ocean returns with new species. In 2023, an expedition to the eastern tropical Pacific seascape catalogued more than 100 potentially new species in just a few weeks of exploration. That rate of discovery, well into the 21st century, illustrates just how large the gap in our knowledge really is. The implications go beyond taxonomy. Unknown species may contain chemical compounds with pharmacological potential that hasn't been explored yet, and in fact, several medications already in clinical use have their origins in marine organisms, including analgesics, anticoagulants, and anti-cancer agents. Every species that disappears before being discovered takes with it a set of evolutionary solutions that took millions of years to develop. The word tsunami calls to mind images of giant waves destroying coastlines. But the most remarkable aspect of the phenomenon isn't what happens when the wave reaches the shore, it's what happens in the open ocean, where it's practically invisible. A tsunami is generated, in most cases, by an underwater earthquake that vertically displaces a large portion of the ocean floor. In deep water, that wave has a wavelength of hundreds of kilometers, but only 30 to 60 centimeters of height. A ship at sea above a tsunami would likely notice nothing at all. The speed of that wave can reach 800 kilometers per hour, comparable to the cruising speed of a commercial airliner. As the wave approaches the coast and the water becomes shallower, it slows down, but the energy has to go somewhere. It concentrates vertically, and the wave grows, sometimes to dozens of meters in height. The retreat of the sea before a tsunami arrives is the most visible sign of this process. It's the trough of the wave arriving ahead of the crest. Coastal populations that recognize that signal have minutes to reach higher ground. A hurricane is, in essence, a heat engine, and the ocean is its fuel. Without the energy provided by warm ocean surface water, no hurricane would ever form or sustain itself. For a hurricane to develop and intensify, the sea surface temperature needs to be at least 26 degrees Celsius, in a layer at least 50 meters deep. The energy released by a mature hurricane in a single day is comparable to the explosion of several nuclear bombs per second. That energy comes almost entirely from the evaporation of ocean water and the release of latent heat as that vapor condenses in the storm's clouds. The ocean also limits hurricanes. As a storm passes over an area, it mixes the warm surface layer with cooler water below, cooling the surface and cutting off its own fuel supply. Hurricanes that move slowly over the same area tend to weaken for this reason, while those that advance quickly over warm waters can intensify with surprising speed. Every few years, the tropical Pacific Ocean goes through a shift in state that alters climate patterns across every continent. That phenomenon is El Niño, and its counterpart La Niña, and together they form the most powerful system of interannual climate variability on the planet. Under normal conditions, the trade winds blow from east to west along the equatorial Pacific, pushing warm surface water toward Australia and Asia, and allowing cooler deep water to rise to the surface along the coast of South America. During an El Niño, the trade winds weaken or reverse. The warm water advances eastward, covering the South American upwelling zone with warm, nutrient-poor water. Strong El Niño events are associated with severe droughts in Australia and northeastern Brazil, intense rainfall along the western coast of South America and in California, an increase in average global temperature, and a weakening of the Atlantic hurricane season. Both phenomena illustrate how the ocean and the atmosphere function as a coupled system, and how a change in one ocean basin can reverberate through the entire global climate. The ocean is full of eddies, not the small and violent kind that appear in films, but giant circular structures that can be hundreds of kilometers in diameter, persist for months or years, and carry water with its unique characteristics for thousands of kilometers. These vortices form when ocean currents become unstable and bend into meanders that eventually close in on themselves. The Gulf Stream frequently forms rings that break off from its main flow, some carrying warm water into the cold interior of the North Atlantic, others doing the opposite. These rings can be 200 to 300 kilometers in diameter and persist for 1 to 2 years before dissipating. It's estimated that mesoscale vortices are responsible for transporting more energy in the ocean than average currents, a fact that was only fully appreciated in recent decades, with the advent of satellites capable of measuring ocean surface topography with millimeter precision. There's an oceanic mechanism that turns marine deserts into zones of abundance and sustains some of the most productive fisheries in the world. When wind blows consistently parallel to a coastline, it pushes the surface layer of water sideways. That displaced water needs to be replaced, and what rises from below to fill its place is cold, dense, nutrient-rich water. Those nutrients fuel explosions of phytoplankton that sustain zooplankton, small fish like anchovies and sardines, and the entire chain above them. The coasts of Peru and Chile, the Northwest African coast, the California coast, and southern Africa are all examples of regions with intense upwelling, and all of them are, not by coincidence, historically rich fishing areas. Upwelling also plays a climate role. The cold water it brings to the surface cools the air above it, inhibiting the formation of rain clouds and creating curious arid coastal climates, deserts that sit right next to the ocean, like the Atacama and the Namib. The presence of the ocean, in those cases, explains the absence of rain. The deepest point in the ocean is in the western Pacific, east of the Mariana Islands. Challenger Deep reaches approximately 10,935 meters below the surface. For reference, Mount Everest, at 8,849 meters, would fit inside the trench with more than 2 kilometers to spare. The first people to reach the deepest point were oceanographer Jacques Piccard and naval officer Don Walsh, in 1960, aboard the bathyscaphe Trieste. The descent took 4.5 hours. At the bottom, even in that moment, Piccard reported seeing a flatfish, indicating that life persisted even under pressure exceeding 1,000 atmospheres. Since then, very few descents have been made. On each visit, something new is found, including, tragically, microplastics in the sediment of the deepest and most remote point in the ocean. One of the most striking images in modern oceanography shows something that seems impossible. Inside the ocean, there are lakes and rivers, bodies of water with a surface, shorelines, and even waves, completely distinct from the surrounding water. These phenomena exist because seawater can have very different densities depending on its temperature, salinity, and chemical composition. In the Gulf of Mexico, depressions in the seafloor filled with extremely dense brine form a sharp surface with their own waves and stable shorelines. These brine lakes are toxic to most marine organisms, but at the edges, where the brine gradually mixes with the surrounding seawater, communities of extremophile organisms thrive. Submarine rivers also exist, currents of dense water flowing along the ocean floor, following the seafloor's contours. The submarine river at the Strait of Gibraltar is a current of dense, salty water from the Mediterranean that flows into the Atlantic along the bottom of the strait, while lighter Atlantic water enters through the top, two rivers flowing in opposite directions through the same channel. At the center of the North Pacific subtropical gyre, there's an accumulation of plastic debris known as the Great Pacific Garbage Patch. It isn't a solid island of trash visible from space, it's a region where the concentration of fragmented plastic, most of it in pieces smaller than 5 mm, is far higher than in the surrounding ocean. Seen from a ship, the surface looks normal. Seen up close, the water is full of translucent fragments that only become visible in samples collected with fine mesh nets. This accumulation is estimated to contain about 80,000 tons of plastic, spread across an area of roughly 1.6 million square kilometers. But recent studies suggest that large quantities of microplastics sink and accumulate in seafloor sediments, in intermediate water columns, and even in the deepest trenches. Fish, seabirds, and zooplankton ingest microplastics, mistaking them for food. The chemical contaminants that adsorb onto the surface of these fragments are transferred into the food chain in ways that are still being studied. The ocean is an acoustically rich environment, and radically different from air when it comes to sound propagation. Water is a far more efficient conductor of sound than air. Sound travels about 4.5 times faster in seawater, and under certain conditions can travel thousands of kilometers with almost no loss of energy. There's a layer in the ocean, between 600 and 1,200 meters deep, where the speed of sound reaches a minimum. This layer, called the SOFAR channel, acts as a waveguide. Sounds emitted at that depth become trapped in the layer and propagate horizontally over immense distances. Blue whales and fin whales use this channel to communicate across thousands of kilometers. The current problem is that the ocean has become significantly noisier due to human activity. Military sonar, ship engines, and seismic surveys for oil generate noise that interferes with the communication and navigation of cetaceans, with documented consequences for their behavior, health, and reproductive capacity. The ocean floor is one of the most complete archives of the planet's history. Layer by layer, the sediment that accumulates over millennia records information about climate, life, ocean chemistry, and geological events with a fidelity that few other natural archives can match. Sediment cores, cylinders of material extracted from the seafloor by probes, are like books written in layers. Each centimeter contains fossils of foraminifera whose shells recorded the temperature and chemistry of the water when those organisms were alive. By analyzing the ratio of oxygen isotopes in those shells, paleoceanographers can reconstruct the average ocean temperature for periods millions of years in the past. Some seafloor sediments contain manganese nodules that grow in concentric layers so slowly, just a few millimeters per million years, that a single nodule can represent tens of millions of years of geochemical history. The ocean isn't just the stage where Earth's history unfolded, it's the place where it was recorded. The ocean absorbs about 30% of all CO emitted by human activities since the Industrial Revolution, as well as more than 90% of the extra heat generated by the greenhouse effect. It contains roughly 50 times more carbon than the atmosphere, making it the largest active carbon reservoir on the planet. But as the ocean warms, its capacity to absorb CO decreases. The very mechanism that has been protecting us is gradually being weakened by the same emissions it's trying to offset. Coral bleaching works like this. When temperature rises above a critical threshold, the symbiotic algae inside the coral begin producing toxic free radicals. The coral expels them as a defensive response, turning white and deprived of its main energy source. If the temperature returns to normal within a few weeks, the coral can recover. If the stress persists, it starves to death. The frequency of bleaching events is what makes the current situation particularly critical. The recovery window is disappearing. Less than 25% of the ocean floor has been mapped with enough resolution to identify relevant geological features. Maps of the Moon's surface have higher resolution than maps of much of the seafloor. The reason is physical. Light and radio waves don't penetrate seawater beyond a few meters. To map the bottom, sonar must be used, a slow, expensive process that requires a ship to physically cover every area to be mapped. The search for new medicines has brought scientists to the ocean floor. The first antiviral widely used against herpes was developed from compounds found in a Caribbean sea sponge in the 1950s. Ziconotide, one of the most potent analgesics available, stronger than morphine and with no risk of dependence, was derived from the venom of a marine snail of the genus Conus. Sponges, soft corals, and microorganisms from hydrothermal vents continue to be investigated as sources of compounds with antibiotic, antitumoral, and anti-inflammatory activity. The skin of sharks, covered in microscopic structures called dermal denticles, reduces turbulence and hydrodynamic drag with remarkable efficiency, inspiring coatings for swimsuits and research into surfaces for aircraft wings. The blue mussel produces protein filaments that adhere to wet rocks with extraordinary strength, resisting the force of waves, and researchers are studying those proteins to develop surgical adhesives that work in wet environments, a medical need that remains unsolved. The human embryo, in its first weeks of development, displays pharyngeal structures that in fish become gills. The composition of human blood plasma bears ionic similarities to primitive seawater. The dive reflex, which slows the heart rate when the face is submerged in cold water, is present in humans without any training. It wasn't learned. It was inherited. The longest mountain range on the planet is completely submerged. The mid-ocean ridge stretches approximately 65,000 kilometers, circling the planet like the seam of a tennis ball. It runs through the center of the Atlantic, around Africa, across the Indian Ocean, and branches through the Pacific. Some points rise above the sea surface and form islands. Iceland is the most extensive example, literally built on the mid-Atlantic ridge. Sound travels about 4.5 times faster in seawater than in air. In 1997, a NOAA hydrophone recorded a sound of unknown origin, intense and at ultra-low frequency, that became known as the bloop. For years it was the subject of speculation. It was later identified as the sound of a large ice sheet breaking in Antarctica. The expression ocean memory isn't a metaphor. The state of the ocean today influences the atmospheric climate of the coming months, because water retains heat far more efficiently than air. Water masses that sank at the poles decades ago carry the signature of the conditions at the time they were formed, and when they resurface in another part of the ocean decades later, they arrive carrying the memory of the past. The seafloor sediments hold records of millions of years of climate history, a library that scientists continue reading, layer by layer. In climate science, there's a concept called a tipping point, a threshold beyond which a system changes state in a self-sustaining way, even if the original cause is removed. The melting of the Greenland ice sheet may be one of those points. As the ice sheet shrinks, its surface sits at lower elevations where temperatures are higher, which accelerates the melting, which lowers the surface further. Models suggest this threshold may be reached with global warming between 1.5 degrees Celsius and 2 degrees Celsius above pre-industrial levels. The global-scale collapse of coral reefs is another identified tipping point. Below a certain threshold of living coral cover, the reef enters a spiral of decline where erosion outpaces growth and the physical structure collapses, regardless of improvements in thermal conditions. What makes these thresholds particularly concerning is their asymmetry. They're far easier to cross than to reverse. Every night, billions of organisms rise hundreds of meters to the surface to feed, and before dawn, they descend back into the darkness. This migration creates a cloud of organisms so dense that it reflects sonar waves as if it were the ocean floor. Sailors during World War II were puzzled by this false bottom that rose at night and sank by day. It was life, billions of organisms migrating in sync, every night, in every ocean in the world at the same time. The ocean contains approximately 10 to the 31st power viruses, making them the most abundant biological entities on the planet by an enormous margin. Every second, trillions of viral infections occur in the ocean, regulating bacterial populations with a precision that no macroscopic predator could achieve. When a bacterial population grows rapidly, it becomes a more attractive target for the viruses that infect it, which suppresses it before it can fully dominate the environment. In 2010, researchers discovered multicellular animals living in completely anoxic sediment at the bottom of the Mediterranean, without any detectable oxygen for tens of thousands of years. Instead of mitochondria, they possessed organelles that generate energy through anaerobic fermentation, something previously known only in microorganisms. If complex life can exist without oxygen on Earth, the requirements for life on other worlds may be less restrictive than previously assumed. Underwater eruptions create new islands within a human lifetime. In 2013, an eruption off the coast of Japan created the island of Nishinoshima, which grew from a few meters to more than 3 square kilometers in just a few years. Submarine landslides reshape the seafloor in a matter of hours, when large quantities of water-saturated sediment lose stability and slide hundreds of kilometers along the bottom. The ocean floor is not a static backdrop, it's a geologically active system. The Earth's climate follows predictable rhythms tied to variations in the planet's orbit, and the ocean is the primary amplifier of those rhythms. Astronomer Milankovitch identified 3 orbital cycles that alter the amount of sunlight the Earth receives. On their own, those cycles produce modest variations. What amplifies them enough to trigger ice ages is the ocean. When insolation decreases slightly, the ocean cools, absorbs more ice expands and reflects more light back into space, a set of feedback loops that turns a modest orbital shift into an ice age. The coelacanth was known only from fossils and was considered extinct for 66 million years. In 1938, a living specimen was caught off the coast of South Africa by a fisherman. It lived at depths between 150 and 700 meters, which explains why it went centuries without being observed by scientists. The Nautilus has a lineage more than 500 million years old, predating the emergence of the first jawed fish. The shark as a group has existed for more than 450 million years and has survived all 5 major mass extinctions in the geological record. The ocean has a documented capacity for recovery when pressures are removed. Whale populations that were hunted to the edge of extinction showed significant recovery after the commercial whaling moratorium of 1986. Reefs that experienced bleaching but weren't subjected to other stresses showed the ability to regenerate within 10 to 20 years. The ocean can recover from a great deal, but not from everything, and not indefinitely. The question isn't whether preservation and recovery are possible. It's whether the collective choices will be made in time and at sufficient scale. There's something deeply unusual about the ocean's place in human knowledge. We're in the 21st century, with telescopes that observe galaxies billions of light-years away, with accelerators that have probed the structure of matter down to unimaginable scales, and yet the largest environment on our own planet remains largely unexplored. Less than 25% of the ocean floor has been mapped with enough resolution to reveal relevant geological features. Most species that inhabit the depths have never been described. Every expedition to the deep ocean returns with something unexpected, a new species, an unobserved behavior, an unpredicted geological structure, a chemical reaction that wasn't in the models. That isn't a failure of science. It's a characteristic of the subject being studied. The ocean is, in that sense, simultaneously the most studied and the most unknown system on the planet. And the distance between what we know and what there is still to discover is, itself, one of the most fascinating things about oceanography. The genuinely open frontier is right here, on Earth, beneath the surface that covers 71% of our world. And as you let all of this gently settle in your mind, there's something comforting in knowing that the world still holds real mysteries, not in distant galaxies, but here, on this planet, beneath the surface of the water that covers most of everything. The ocean that gave rise to life. The ocean that still lives inside our bodies. The ocean that regulates every breath, every rain, every temperature we feel anywhere in the world. An ancient, patient, and extraordinarily complex system that existed long before us, and that, with the right choices, can continue existing long after. Let these thoughts dissolve slowly, like salt in water, like light fading as the depth grows. And as you drift into a deep and restful sleep, remember to subscribe, so these stories can keep finding you, night after night. Sleep well, and sweet dreams.